Knox Game Design, May 2022. Enemy Behaviors.
Welcome everyone to Knox Game Design for May 2022. My name is Levi Smith. So this month's talk is going to be about enemy behaviors. So I got a few examples and just a basic overview of some simple enemy behaviors. Not saying that this is all the enemy behaviors that there are in games, but just a few just to get people started. So first of all, what I did to prepare for this is I just created a basic enemy class. An enemy is going to have a position. In these examples, I'm just going to be doing a 2D game. So they're just going to have an X and a Y position and also a width and a height. And in most cases, they're going to have a velocity, an X and a Y velocity, and a sprite image associated to each of the enemies. So the first one, this is the simplest one, is just moving an enemy back and forth. And there's two different ways to handle this. And I'll say anybody that's wanting to get into game development, this is where I recommend getting started. Just getting a player moving around, then just getting an enemy to move back and forth. So there's two ways that I think that you could handle this. First of all, you're going to have that X velocity that's going to be telling your character how fast to move. And this could also apply to enemy moving in multiple directions. But in these examples, I'm just going to be looking at moving in the X direction on the X axis. So like the first, I'm trying to use some real world examples up here. So you got games like Galaga where you just have the critters, the space aliens or whatever moving back and forth. And the second example, you got a Goomba down there. But for the Space Invaders type example, we're going to use a timer based to tell the enemy when to start moving in the other direction. So we're going to need a float variable that holds the countdown, and also another float variable, and float just being a floating point number value, like a real number. You're also going to need a max countdown. You could possibly make the max countdown a constant where it doesn't change, but you could also make it a variable where you could potentially change it as the game progresses. But either way, you just need something to track what the max countdown is. So what we're going to do is we're going to set the countdown for the velocity change to the max countdown on startup. And then on every update, we're going to subtract off the delta time. So basically, delta time is how much time has elapsed since the previous frame. So we're going to subtract that off. And then once that countdown value gets to 0 or less than 0, then we're going to flip the X velocity. So basically, we're going to take vel X and assign vel X times -1. So if your enemy was moving in a positive X direction, moving from left to right, then it's going to make it go right to left. Or if it was moving right to left, then it's going to make it move left to right. So that multiplying by -1 is basically just going to flip the X velocity. In some languages, you might see like velocity star equals -1. That will also flip it. And then once we do that, we're just going to add that max countdown to the countdown value to reset it. You could just set the countdown to the max countdown. It kind of does the same thing, but this adding and assigning the max countdown kind of takes into account if you went under 0. So you're not going to go to the full countdown. You're just going to go to that maximum countdown value again. But either way, that's going to get an enemy moving back and forth based on time. The other way you could handle this is like in the second example, I have a Goomba down there from Super Mario Brothers. So it doesn't care about time. It's going to use a collision-based back and forth. So as this enemy is moving along in the X direction, when it collides with an object, a block, a solid object, then that's the time it's going to start moving in the other direction. So it's going to use the same velocity X, gets velocity X times -1. So, and I also mentioned down here, this is kind of a simplified version of a bounce. I'm not going to go into like the details of how to calculate the angles and everything for a bounce, but this is kind of just like a specialized case when an enemy's coming in at a 180-degree angle or a 0-degree angle, then it's going to flip 180 to 0 or 0 to 180. So I do have some, and I was trying to decide if I wanted to do the demos at the end or with the presentation. So I think I'm just going to do them with the presentation. So first of all, I got a game manager class. It just kind of runs the whole demo. We got some enemies, some blocks, and a player. I went ahead and put the player in the list just so I keep everything kind of the same. We got some texture 2D, some simple sprites that I made, and I think I made those in Spriter. Yeah, I made those in Spriter. And some fonts. And oh yeah, by the way, I did this in Monogame, a lot like X and A. You can actually see these characters in this content MGB. Oh, I actually can just see the output. But that's where the images are loaded in right there. And oh, by the way, I think a year or two ago I did a talk, Knox Game Design presentation on Monogame. So if you want a tutorial on Monogame, then I recommend looking at that. And also, this could be implemented in Allegro, SDL. If anyone out there has some spare time, all this could be converted to any of those other game environments. But yeah, we basically have an initialize right here where we're setting up the enemies and the player and the blocks and load content. This is just basically loading in those images, sprite images, and the font. I'm not going to go into detail on the font. It's not very involved. And here's our main updates. We're handling the keyboard input and updating the enemies and updating the players. And of course, blocks don't need to be updated. They're just static objects. And this is a simple player control right here. So basically, when you press left, right, up or down, it's going to move in those directions, set the player velocity in those directions, which if you press up and over at the same time, then you're going to go a little bit faster. So this isn't perfect. This should be cleaned up right here. But yeah, basically we have different screens for each of the demos. Once you press space, press the space key, then you're going to go to the next screen. It's just going to call this load screen. And here's the draw. We're going to draw the blocks, the enemy, and the player right there. And each of those types has a draw method for drawing those to the screen. And here's where we're displaying. I should have showed the demo probably first and then came back to this. But yeah, here's where we define our screen. So for each of these screens, for each of the demos, we're going to instantiate different types of enemies. And in some cases, blocks, and in some cases, in one case, a player. That's what that's doing right there. And I have just a handy, this could have been put in a different class, but a handy check collision. I talked about 2D collision 2 months ago. So if you want to know all the details about this, check the Knox Game Design for 2 months ago. I believe that was March 2022. So yeah, here's our enemy, simple enemy class right here. Like I said, you got an X and a Y position. I went ahead and made these floats because sometimes you have weird things happen if you make these ints. Sometimes you can have a fraction of a number for an X and a Y position. Made the width and height both ints, and then you got the velocity X and Y. Reference to that game manager class, so you can kind of poke back into that, grab back into that if you need. One demo requires access to the player object, so that's helpful right there. And here's our constructor, just an enemy. Update, I made it abstract, so I'm going to have all these subclasses for these different enemy types with different behaviors. So I'm leaving it up to the subclasses to implement the update method, and also made the draw method virtual. So by default, it's going to just draw, but in some cases, I may need a specialized draw method. I think in most of them I do use a specialized draw, so that can be overridden. And then I just have a set position for setting this up. So that's all there is to it. Going to run this. Like I said, this is Monogame. This is Visual Studio 2019. So yeah, here's our back and forth demo right here. So this is the timer based right here. So we got the first enemy. He's moving at a velocity of 2, And basically I have a constant in there for the unit size. So I'm using 64 pixels for a unit, just to make things a little bit simpler. Trying to deal with pixels can be a headache at times. But basically this enemy is 1 unit wide by 1 unit tall. So you can see here I have the countdown variable, and when this countdown is set to the value until it's going to change. When that reaches 0, then it's going to flip that velocity. And then I have a max countdown variable. So here for the first enemy, it's 2. So that's going to go 0 from 2 to 0. And each time it hits 0, then it's going to flip the velocity from 2 to -2. It's going to multiply by -1. Second enemy here, he's also moving at a velocity of 2, but his max countdown is 1. So it's going to count down from 1 to 0 every time it hits 0. Then we're going to flip that velocity. And then the final enemy down here, he has a velocity of 4 by default, and he also has a max countdown of 2 like the first one. So every time that countdown hits 0, it's going to flip from 4 to -4. But you can see the top and bottom enemies both have the same max countdown. But since the second enemy has twice the velocity of the first enemy, he's going to go a lot farther. So basically that your velocity and your max countdown are going to determine how far your enemy is going to go before they flip back. So I'll close that real quick. So yeah, I have all the subclasses down here. So basically that enemy was back and forth timer. So he's going to subclass enemy right there, and he's going to have these, here's our 2 variables, our countdown and our max countdown. And basically you're just going to have an empty constructor that calls the super constructor and passes in the values that it wants, the sprite and the reference to the game manager. Here we're setting the countdown, set countdown. That basically tells it how long is the max countdown, and update. So we're overriding the update method. So like I said in the slide, for every frame, we're going to subtract off the delta time from the countdown. And then when it's less than or equal to 0, then we're going to, so I use the star equals right here. We're going to flip the x velocity, and then we're going to add the max countdown to reset the countdown value. And then on every update, we're going to add x and the delta time, move it along. And yeah, this draw method just draws the enemy, and this is why I'm overriding draw, so I can add in the debug values down here. But yeah, that's all there is to it. You just get a simple enemy moving back and forth. And I think if anybody can get this working, you've probably done more than probably 95% of the people who've wanted to make a game. Just get an enemy moving back and forth. And that's all there is to that one. So I'm going to go ahead and start this guy up again. And the second case that I've talked about was like the Goomba. This is the collision-based back and forth. So first enemy, kind of the same thing going on here. The first one has a velocity of 2. He bounces back from 2 to -2. The second one also has a velocity of 2, but the blocks are a little bit closer together. So it kind of looks like he has more energy bouncing around and everything, but he's moving at the exact same speed as the first guy. He's just bouncing back and forth a lot more. Then the third guy down here, he has a velocity of 4, so every time that he collides into a block, it's going to go from 4 to -4. So that enemy is subclassed in enemy back and forth collision. And oh, by the way, I'll put this out in a code repository where everybody has access to this. If anybody wants to look at this code, it'll be on Knox. Link to it will be on knoxgamedesign.org. So yeah, here we go. So same thing going on here. We're subclassing enemy with enemy back and forth collision. On the update, we're going to say has collided is false. And then we're going to add on the delta time to the x value. And then we're going to loop through all the blocks. So that's why I need a reference to Game Manager to get a reference to all the blocks. And then we're going to check the collision between this enemy and the block. So that's that utility method I was talking about. So this is going to check to see if the enemy collided with the block or not and return true or false, a Boolean value. So if it has collided, then we're going to change, or no. So yeah, one thing you got to watch out for is you got to kind of check and see if it did collide. If it did collide with the block, then you kind of got to move it back out of the block. You don't want to get stuck inside the block. So that's what I'm doing right here. I'm just kind of subtracting off. You could check on the next frame, but here I'm checking on the current frame. So if the enemy moved inside the block, we're just going to push them back outside the block. And then we're going to change the velocity right there. There's a few different ways you can handle this right here. You could push the enemy right next to the block, or you could move it to the previous position before it went into the block, which is what I'm doing here, is just moving it to the previous position where it was at. Just to ensure that we're not getting anything stuck inside of a block. But usually if this thing's moving at 60 frames or 30 frames a second, you're not really even going to notice that, whether it's right next to the block or not, unless it moves all the way up and stops, which isn't happening in this case. And yeah, here's the draw method right here. So we're just drawing the enemy and the velocity right there. So that's all there is to it. I did the timer demo first because it's a little bit easier to get up and running because you're not dealing with collision. But the collision is pretty simple as well. Now, there's a lot of game frameworks, development environments out there, such as Game Maker, and a lot of this is already implemented for you. I think it's the collision method is called place meeting. Unity and Unreal and all the other ones, they have collision methods already written for you, but I just want to show how to implement this from scratch yourself with a collision method, which isn't much. It was like 8 lines of code. Actually, it's really 3 structured lines of code. But you got this one if right here that has your 4 different checks. Okay, so back to the presentation. So that was just the first behavior. And by the way, it's like I'm just kind of implementing these behaviors inside of the enemies, which does good for a simple game. But if you're going to do anything really involved, and I'll get into this a little bit later, you'll probably want to have like a behavior class that you just attach to the enemy or an interface, which would probably work a little bit better, not having the logic right inside the enemy's update method. So here's the second enemy that I was kind of thinking about with old games, like Metal Gear for the NES is the example that I have right here. Is when you get close to an enemy, that enemy is going to follow you. So I call this proximity, alert, and chase. So what you need here is an alert distance for the enemy, which will be a float, then an is chasing Boolean value, whether or not the enemy is chasing the player. So basically, it's just going to check and see if the player's position is less than or equal to, however you want to handle that, then the alert distance. And it's going to set is chasing to true. Or if we're in the update method and we're already chasing, if the player's position is greater or player's distance is greater than the than a set value for stop chasing, then he'll stop chasing. I think I put that. Yeah, that's chase end conditions out there. So as the enemy is chasing the player, if on every update, basically we're going to move the enemy toward the player, and I just have a move towards method right there, which I have implemented in code. It's just a simple chase method right there, and we're going to multiply that by delta time, multiply it by the speed time of delta time, so it is a continuous velocity toward the player. It isn't based on the frames or anything like that. So to get the distance, and I'll also say this does kind of a circle of alert around, which I don't have a display of this in the code or anything. But this detects like within a certain radius if the player gets close. Now, if you play a game like the later Metal Gear games, they have a cone, like a slice of detection, which I don't have implemented into this. I think that's used in quite a few games. I'm not going to go into detail about how to implement cones. This will just be a simple circle. So if the character is like within the alert distance on the right or the left, no matter which way the enemy is facing, they're going to get alerted. And to calculate that distance, we're going to go back to the old Pythagorean theorem. A squared or C squared equals A squared plus B squared, which is C equals the square root of A squared plus B squared. And the A squared value is just going to be, and we've got our triangle down here. So to get the distance between the character and the enemy, that's going to be C. So to get the value of C, we're just going to take the square root of both sides. So C equals square root of A squared plus B squared. But to get the value of A and B, that's going to be the differences between your X value, the X of your player and the X of the enemy, and the difference between the Y values, the Y value of your player and the Y value of your enemies. And by the way, you'll see this right here to the 1/2. Actually, I think there should be a squared on each of these right here. I'll change that. So yeah, distance equals the difference between the x's squared plus the difference between y squared. And all that, we're going to raise it to the 0.5 or the 1/2, which is the same as square root. So if you're in a game development environment, if they don't have a function for square root, just raise it to the 0.5 power. That'll give you the square root. So yeah, that's great. So that tells the enemy when to start chasing the player. And by the way, this doesn't account for if there's like a block between the player and the enemy. There's like different search path algorithms like A star and all that, which you probably want to look into if you get really deep into this. This is just assuming there's no objects between the enemy and the player, and this is how you can handle it. So yeah, that'll get the enemy chasing the player. And oh, by the way, you want to have it so the enemy's velocity is less than the max velocity of the player, because that will give the player a chance to escape the enemy, unless you just want to have so that's impossible to escape. But yeah, make sure your player's run speed is faster than the enemy's run speed, just so you give the player a chance to escape. If not, the enemy will just chase the player forever. So we got the enemy chasing the player. So when does the enemy stop chasing the player? So 2 ways to calculate this, or 2 ways to handle this. I think I talked a little bit about this a minute ago. The distance from the player, you can have a constant value for the enemy that says, hey, when the player is greater than a certain distance from the enemy, then stop chasing. And that's what I have down here. The constant float. If distance between the player and enemy is greater than the stop chasing distance, then set enemy is chasing to false. The other way to handle this is a timer base. So you could have a chase countdown float and a maximum chase countdown. So whenever the enemy starts chasing the player, then that countdown gets set to max countdown, then starts counting down. On each frame, you're just going to subtract off delta time. So this is going to say after a certain period of time, even if the enemy, no matter how far the player gets away from the enemy, the enemy is still going to chase until that countdown has hit 0. So here's the demo for that. So I got my little player here. It isn't perfect, but you can see the one at the top. As I move the player around, it's going to calculate the distance between the player and the enemy. And oh, by the way, you probably want to use the center of the player and the center of the enemies. By default, like in Monogame, your X and Y position is going to be in the upper left-hand corner. So you just want to add on half the width and half the height, and that'll get the center of the player, and also do the same for the enemy. Otherwise, it's not going to be a perfect alert circle around the enemy. It's going to be based on that upper left-hand corner. So yeah, you can see these enemies down here, like distance 5, 4, 3. So the alert distance for that top enemy is 2. So when I get within 2 units, then he's going to start chasing me. And you see that is chasing bullying going from 2. And then when I get further than the in chase distance, then it's going to stop moving. It's going to say is chasing the falls. And yeah, so there isn't any concept of health or anything like that in this game yet. That would be later on. So yeah, the enemy's just going to keep chasing until it gets right on that player right there. And until the player gets 3 units away, it's going to keep chasing. So the second one, if I can get away from him, the second one, this is the one at the bottom. He's based on time. So he's got a max chase countdown of 5. So no matter how far away I get from that enemy, he's going to chase until that countdown gets to 0. So I can be close or far away, it doesn't matter. And even if I'm still within that chasing alert distance, then he's going to keep chasing. But yeah, once that chase countdown hits 0, he's going to stop. Yeah, so that's basically 2 different ways to handle chasing of enemies. Go back. Oh, let's look at the code before we go on. So I have that one in enemy chase in distance. So yeah, so here we got the alert distance 2, the is chasing boolean, the chase in distance is 3. So on every update, if he's not chasing, then we're going to get the chase distance, and chase distance is defined right here. So this basically, and this is where I'm doing the Pythagorean theorem right here, the square root of the difference between the x's and difference between the y's. So this just calculates that distance. I'm going to divide by the unit size because by default it's using pixels, but I just want everything in 64 pixel units. We're going to return that from get distance. So if that distance is less than the alert distance, we're going to say is chasing to true. And otherwise, if he's already chasing, then we're just going to do a simple chase. We're going to set the speed to 0.5 units, and we're going to go, if the x is less than x, player's x, and we're going to move in the positive direction. If it's greater, this isn't perfect right here, really. We should be calculating the angle between the enemy and the player and normalizing that to get a true, like, smooth velocity. But this is just simple for a demo right here. So the point is we're going to add the x and y velocities. And then if the enemy's already chasing, we're going to get the chase distance, distance between the enemy and the player. And if it's greater than the in chase distance, then we're going to set is chasing to false. So that's really all there is to it. And here's where we're drawing the image and the debug values. So that's a really simple chase right there. And really, if we're making this into a full game, we would check and see if the enemy is collided with the player, and then either like subtract off some health and then add iframes and all that good stuff. So that's the enemy chase ending by distance. Here's the enemy chase ending by timer. So we got the same alert distance, is chasing boolean, and then we got the max chase countdown and the current chase countdown, chase in countdown. And basically we're kind of doing the same thing. If the enemy's not chasing and you get lower or equal to the alert distance, when we're going to start chasing, and we're also going to set the chase in countdown to the max chase in countdown. If he is already chasing, if his chasing is true, then we're going to move the enemy toward the player. That's what this is doing right here. And that's what that's doing right there. And then we're going to subtract off from the chase countdown the delta time. And once that chase countdown gets to less than or equal to 0, then we're going to set is chasing to false. And this is just where it's drawing and displaying the debug right there. So that's really all there is to it to get a simple chase working. I mean, not too much. And oh, by the way, I do have the player class right here. So this is the player, and kind of like an enemy, it's got an x and a y, width and a height. And all we're doing is adding velocity of x and velocity of y based on the player's input, which is captured actually in the game manager. You could put that actually in the player, but yeah, we're handling the player controls right here in game manager. So that you could put all this actually in player, and then have game manager say, player, go update yourself based on the input. And by the way, this only is handling keyboard. You'd really want to have it handle gamepad as well. So that's it for the chase. Oops. Go back. Do a shift F5. So yeah, here's like a random enemy move right here. I call this move, stop, and chase direction. So it's kind of like an Octorok in Legend of Zelda. So we got the same, like a move countdown, a max move countdown, a stop countdown, and no, there's a typo right there, max stop countdown. So before we start moving, we're going to have a function called change direction. We're going to set the X velocity and the Y velocity. So what I'm doing right here in this example, I'm just using a random value from 0 to 4. And those are whole integers, 0, 1, 2, 3, 4. Then I'm multiplying those by 90 degrees or pi over 2. I think I'm using pi over 2 to get 0, 90, 180, and 270. So this is going to make the enemy move up, down, left, or right. So yeah. So I'm setting the X velocity and Y velocity using the speed of the enemy times the sine or cosine of the angle. That 90, 180, 270, or 0. Okay, so yeah, so the enemy's moving, and we're going to set that max countdown value. So when that, on each frame, each update, we're going to subtract off delta time from the countdown. If the countdown is less than or equal to 0, then we're going to change the direction. Actually, this is when the enemy's waiting right here. So if the enemy's waiting, then we're going to subtract off the wait countdown. When it gets below 0, we're going to change direction, then set the moving countdown to the max moving countdown. I think I'll also mention here, you could have just like one countdown for both moving and waiting, but to keep things simple, I just created 2 separate countdowns. One for moving, one for waiting. Then you're going to have a max wait countdown and a max move countdown. Now you could have the wait countdown and the move countdown be the same value, but this handles the case if they're different. So you could have an enemy move for 2 seconds, wait for a second, then start moving again for 2 seconds. And you could actually even randomize the move, max move, and the max wait to make it look a little bit more organic. Make it a little bit less predictable. And down here I have the moving countdown when it is moving, so we're just going to add on the X and Y velocity, set the moving countdown, subtract off the delta time, and when the moving countdown gets less than or equal to 0, then we're going to set the wait countdown to the maximum wait countdown. So really could even have a Boolean to track whether the enemy is moving or not, if that makes things simpler for you or for whoever. You could have a Boolean track those as well, but that seems like it's a little bit redundant, because if the wait countdown is greater than 0, then you know the enemy's waiting. If the move countdown is greater than 0, you know the enemy's moving. So having an extra Boolean to track that just really doesn't seem necessary to me. So let's look at the example that I have here. Start this one up. Okay, so here we go. So we got 3 enemies. They're all kind of just moving around. I will say I did add a little extra code to keep the enemies from moving outside the screen. I guess you can kind of think of that as another behavior. Another good tool to look at if you're trying to learn behaviors is Stencil, where it has kind of like a plug-in behavior, and it does have like a stay within screen behavior. So I recommend Stencil if you're just getting into game development. But yeah, we got the 3 enemies here. 2 of these seem to be going toward the side, but we have like the one here in the middle. He's going to move for 0.25 and then stop for 0.25. So he's kind of just has an equal move and stop. Can't see these other guys. They've moved so far over. Let me re-roll this guy here. So this other one here, he has a move countdown of 1 and a stop countdown is 5. So he's going to move for a second, then stop. And I think I set all the velocities just to be 2. So they're going to move 2 units each time. And the one over here, he's so far to the edge. What was he? Yeah, so he moves for 1, then he stops for 2. So we see the 2 different countdown variables here. So every time it hits that, every time the top one hits 0, then it's going to stop. Every time the bottom countdown hits 0, then it's going to start moving again. So I'll just say is like, okay, these can actually have the same velocity, but the one on the bottom looks like it's a little bit more active or has more energy just because he's moving and stopping more, but really they're kind of moving at the same exact speed. So you can kind of make an enemy, like if you have a slug enemy or something, you just have him wait longer or change velocities less frequently to make an enemy. Because all these enemies are the same, but they kind of feel different just because one's stopping and moving more often. So let's look at the code for that one. So that is move, stop, change direction. So like all the other ones, it's going to subclass enemy. So I got the move countdown, I got the max move countdown, the stop countdown, and the max stop countdown. And then I got a random variable R that's just going to generate those random 0, 1, 2, 3 for us. So when we instantiate this enemy, we're going to create the new random variable, the new random type. And then we're going to change the direction, set up an initial direction. And basically, whenever this is created, we're going to set the max countdown and the stop countdown, or the max move countdown, max stop countdown. And then on every frame, if the move countdown is greater than 0, we're going to move this guy based on the x velocity and y velocity and delta time. Then we're going to subtract off the move countdown by delta time. And then if the move countdown is less than 0, then we're going to set the stop countdown to the max stop countdown to say, hey, this guy stopped, which is signified by a stop countdown of greater than 0. Otherwise, if the enemy's not moving, if he stopped, then we're going to subtract off delta time from the stop countdown. Then if the stop countdown is less than 0, then we're going to set the move countdown to be the max move countdown to signify, hey, the enemy is moving. And then once he starts moving, then we want to change direction. So that change direction is handled down here. So this is where we're generating the random number 0 to 3. 4 is exclusive right there. Then we're going to multiply that by math.pi divided by 2, which is 90 degrees in radians. So yeah, so the speed is 1 time unit size, so 64 pixels. And this is where we're getting the x and y velocities. We're just going to take the speed and multiply it by the cosine of the angle for x. Then we'll take the speed and multiply that by the sine of the angle to give us the y velocity. And then here we're just drawing them right there. That's all that's going on there. And oh yeah, here's that little bit of extra code. You can just kind of ignore this, but this keeps the enemies from walking off the screen right there. So really, this should have been in a separate method or something right there. But yeah, that's all there is to it to get an enemy moving around, kind of like a little Octorok type guy. So yeah, this is the most complex one right here that I wanted to do for this talk, and I'm just doing 4 behaviors. And this is kind of like an enemy with children objects. I was kind of like thinking of the Patra in Legend of Zelda, one of the boss type enemies, mini boss enemies at the final dungeon. So this enemy has like a core, the main enemy. Then it has like a number of other child enemies orbiting around the main enemy. So to do this, well, what do we need? We need the lifetime. That's going to tell each of the children what position they need to be at. The total lifetime of the enemy. A list of the children objects, the orbit radius, and the orbit speed. How fast are these enemies, the little children enemies, going to be rotating around? And also, how far away are they going to be rotating around? So the x value of the child is going to be the orbit radius times the cosine of the orbit speed times lifetime plus the angle offset. So each of these enemies is going to have little child enemies. They're going to have an angle, an offset angle to evenly space them around the parent enemy. So that's what that angle offset is. You could theoretically like have each child have its own lifetime and calculate it that way. That's not the way I decided to implement it in this, but that's a alternate way of doing this, having each child with a lifetime. But this, I'm tracking the lifetime in the parent enemy right here. So to get the Y value, it's the same thing. We're going to take the orbit radius, multiply that by the sine of the orbit speed times the lifetime. That's going to give us the Y value plus the angle offset. And here's where I have the angle offset right here. The child number divided by the child count times 2 times pi. So that's going to tell you, based on the child index, how far around that circle that child's going to be. And I also mentioned down here, we could actually take, and I'll hold off on that. Another example of this is kind of like in Mega Man 2. You got the Woodman. He had like little leaves that orbited around. So that's kind of like 4 children orbiting around the parent right there. And that's actually a power-up as well. So let's go back to our demo and play this. So here's like 3 orbiting enemies, or 3 enemies with orbiting children. So the one in the upper left-hand corner right here, he has 8 children, and they're orbiting at a radius of 2. That's 2 units. So that's going to be 128 pixels because each unit is 64 pixels. And they're orbiting at a speed of 0.5. So that means for every 2 seconds will make a full orbit, but in 1 second. So the orbit speed tells you in 1 second how many times around is that child going to go. So in 1 second, it's going to go half the distance around the parent. So if you just look at 1, you go 1, 2, 3, 4. So for every second, it's going to go halfway around. So for the second guy here, we got 10 children, and they're going at an orbit radius of 3. So they're going to be a little bit further out than the parent right here. And their orbit speed is going to be 0.25. So for every 1 second, they're going to go a quarter wave around. They're going to go 90 degrees. So if you just look at 1, 2, 3, 4. So it takes 4 seconds for a child to go all the way around the parent. And then the one here at the bottom, it's kind of like the Woodman, Mega Man Leaf Shield. A little bit closer, he only has 4 children. They got an orbit radius of 1. And oh, by the way, it's 1 from the center of the enemy to the center of the child right there. You got to handle that. And the reason I did this example, they got an orbit speed of -1. So that means instead of going clockwise, they're going to go counterclockwise. They're going the other way. They're going they're going the opposite direction of an analog clock would. So yeah, let's look at the code for this guy. So I got the enemy orbital. So here we got the lifetime, the orbit radius, the orbit speed, then the list of children. And I did make a note, one orbit speed equals 1 orbit every second. We're going to set, when this gets instantiated, it calls the constructor, and it's going to set the lifetime to 0. Then for every update of the parent, then we're going to add on the delta time since the last frame, then multiply that by math pi times 2f. I could have handled this a different way, but I just went ahead and multiplied that out right there in the lifetime. So then for every child for that parent, we're going to calculate that angle. We're going to use the angle offset, the default offset of that enemy, which is basically the index of that child divided by the child count times 2 pi, which is 360 degrees. Then we're going to get the center of the parent right here. So basically we're taking the x and y and we're adding half the width and half the height. And then, so for the position of the child, we're going to take the center of the parent plus the orbit radius times cosine for the x position of the lifetime times the orbit speed, then add the angle offset. Just like I said on the slide. So that gets the x position to y. You're going to take the y position of the parent, add the orbit radius times the sine of lifetime times the orbit speed plus the angle offset. And here we're just centering it up. We're going to subtract off half the width and height of the child. Otherwise, it's going to be anchored at the upper left-hand corner of the child. Then we're just going to call for the child, basically in our main enemy class, called set position XY. So in this case, we're kind of overriding the default behavior of an enemy, so it doesn't have any X velocity or Y velocity. We're going to manually, from the parent, set the position of the child. Yeah, so this is all for the parent right there. Okay, that's drawing him the default debug right there. And set children. I forgot where set children. Yeah, I think that gets set in the constructor, but that's just going to assign, I believe, the child to the parent list right here. Yeah, so basically we're taking in the number of children, the orbit radius, and the orbit speed, and we're instantiating all the children right here, then assigning those to the children list. And then we're just adding that to the game manager enemies just because it is an enemy and we need these children to draw themselves. So in the main game manager class, it goes through all the enemies and calls draw and update. So we need these to be draw. That's why we're adding them to the game manager right there. A little technicality. So we do have a separate enemy class for the orbital child, which, yeah, basically does nothing because the children have really no logic or anything in themselves. They just have a X and a Y position and a width and a height. So that's just to have that in its own class right there. So that's basically it. So I have one more demo to make this look a little bit more like the Patra in Legend of Zelda. You can make the orbital distance a variable. So here we got 8 children, and the orbit radius goes from what is it, 1 to 3. So here it goes all the way down, then when it gets all the way out, then it's 3, and then it starts going back down. But you just need one extra variable to track like the current orbit radius and then the min and max radius. So this is kind of like the pattern in Zelda, how it goes out and comes in and goes out and comes in. All the other stuff is pretty much the same. And I also went in and added the bouncing from, going back to the first example, moving left and right based on a timer. So just to give it a little bit of movement right there. So yeah, orbital children, variable radius plus moving. So that's the last one that I have. So yeah, this is all for the parent. So I have a min orbit radius and a max orbit radius and a current orbit radius, and then the change velocity. That means whether the orbit distance radius is increasing or decreasing. So it's kind of the same thing going on, just in the constructor we set the max countdown. So I also went in and added the left and right timer. Really, like I said earlier, this should be like in its own behavior interface where you could plug in the left and right moving. But I went and just, for time's sake, I just kind of plugged it in here, right here. So yeah, that's what we're doing, setting the max countdown to 3. So every 3 seconds it's going to move in the opposite direction the parent is. Yeah. So I kind of have updated. I kind of broke this out into the 3 different types of behavior. So we got the back and forth timer right there that just moves it right to left on update. Then we're going to update the orbital children. So this is the same exact code from the previous example of updating the children. So yeah, this really should be like in a standard behavior right there, so we don't duplicate code. And so the really only thing that I'm adding is the update orbit radius. So if you go to update orbit radius, the current update orbit radius is going to get the orbit change velocity times delta time. Then if the current orbit radius is greater than the max orbit radius, then we're going to flip. We're just going to make the orbit change velocity the negative orbit change speed times -1. Otherwise, if the orbit radius is less than the minimum orbit radius, then we're going to change the orbit radius velocity to the standard orbit change speed. So yeah, basically speed is the absolute value of velocity. So the velocity is going to be positive or negative, the speed value. So yeah, that's all there is to it. I mean, not a lot really. But it just kind of goes to show you can get some really interesting enemy behaviors with not a lot of code. Yeah, so that's it for the presentation. Back. That's going to wrap it up for Knox Game Design, May 2022. Appreciate everyone out there listening and watching. As I said before, I'll post this code out online. You should be able to get it on knoxgamedesign.org. So I plan on being back in a month. Thanks everyone for listening and watching.